For our last video of Chapter 4, we're going to take a look at the classification of subgroups of cyclic groups. We'll start by taking a look at the fundamental theorem of cyclic groups, and that includes all three of these bullet points. First, every subgroup of a cyclic group is cyclic. Now keep in mind that does not mean that if a group has cyclic subgroups, that the group itself is cyclic. We looked at that when we looked at U8. U8 is not a cyclic group, but does have cyclic subgroups. So back to this theorem, every subgroup of a cyclic group is cyclic. If the order of the cyclic subgroup generated by A is n, then the order of any subgroup of the cyclic subgroup generated by A is a divisor of n, and again that means as a factor goes into n. For each positive divisor k of n, the cyclic subgroup generated by A has exactly one subgroup of order k, namely the subgroup A to the n divided by k. So let's take a look at an example because that's kind of a lot going on. So we have a cyclic subgroup G generated by the element A, and we're given that the order of that group is 20. So they could have written it like this. They could have also written it just like this. We want to know the subgroups of G and their orders. So how is the fundamental theorem of cyclic groups going to help us with this? Well, what we need to do is we need to think about 20 being n. So this is 20 in our example that we're looking at. Then the order of any subgroups is a divisor of n. So let's think about what divides 20, or factors of 20. 1, 2, 4, 5, 10, and 20. Then it says for each positive divisor, so these are the divisors that we just generated or that we just talked about. For each positive divisor, the group, the cyclic subgroup generated by A, has exactly one subgroup of order k. So we're going to have one subgroup of order 1, one subgroup of order 2, one of 4, one of 5, one of 10, one of 20. How do I find those subgroups? I take n divided by k. So what's 20 divided by 1? Well, that's 20. So I've got a subgroup, A20, and that's going to be my subgroup of order 1. So what happens when I generate with A20? I get E. And that's all I have. And again, that's order 1. So why is that 20? Well, because A to the 20 would be, in a group of order 20, would be back to the identity. All right, now let's take 20 divided by 2. So I'm going to have a subgroup of order 2, and that's going to be A to the 10th. So A to the 10th is going to give me A to the 10th, and then E. So this is order 1, and this is order 2. So now we've used 1 and 2. Now let's take 20 divided by 4. So again, this is going to be order 4, and it's going to be found by A to the 20 divided by 4, or 5. So A to the 5th is going to give me A to the 5th, A to the 10th, A to the 15th, A to the 20, which is E. That's my order 4. So we get the idea. All we're doing is division. So now we've used 4. Now we'll take 20 divided by 5, which is 4. So I'm going to take A to the 4th, and it's going to have order 5. So A4, A8, A12, A16, back to the identity. So that's order 5. Now let's look at 20 divided by 10. 20 divided by 10 gives us 2. So this is going to be order 10, and it's going to be A to the 2nd. So again, that's going to give me A squared, A to the 4th, A to the 6th, and so on, A to the 18th, E. So there's 10 total items, so the order is 10. And then the last one, 20 divided by 20, which gives me 1. So a, or just a to the first, that's going to generate everything, right? Because we're going to get a squared, a to the third, a to the 19th, a to the 20. Oops, a to the 20, which is the identity. So again, this is order 20 and generated by a to the first. This one was order 10 because there would be 10 elements in that set. Now, we do have a corollary related to the fundamental theorem of cyclic groups, and this is specific to Z sub n. So if you'll recall, Z sub n is a group under modular addition, and it's all of the values from 0 up to n minus 1. And this corollary says for each positive divisor k of n, the set n divided by k, so that's going to be a cyclic subgroup generated by n divided by k, is the unique subgroup of z sub n of order k. And that's the only subgroups of z sub n. So again, this is for each positive divisor. So before we look at the example, let's think about for Z24, what are the divisors? Well, the divisors would be 1 and 2 and 3 and 4 and 6 and 8 and 12 and 24. So for each of those, we're going to have a subgroup of n divided by 1. So that's 24. We're going to have a subgroup n divided by 2. So that's 12. We're going to have a subgroup n divided by 3, which is 8. N divided by 4, which is 6. N divided by 8, which is 3, n divided by 12, which is 2, and n divided by 24, which is 1. So again, for each positive divisor of n, the set n divided by k is the unique subgroup of order k. So now we're asking the question, in Z24, list all the generators for the subgroup of order 8. So the subgroup of order 8, that's where we got this. Right? We said subgroup of order 8 says 24 divided by 8 means 3. So 3 is a generator. Now, what we're going to do is think about a theorem that we learned in our last video that says, okay, well, if you know that 3 is a generator, then the other generators are going to be in the form of 3j, or I, or whatever variable you choose to use, where the GCD of 8 and that value is 1. In other words, we're looking for values that are relatively prime to 8. So what values would that be? Well, 1 is relatively prime to 8, which is where we get this one. 3 is relatively prime to 8. 5 is relatively prime to 8, and 7 is relatively prime to 8. So if 3 is a generator, what are the other generators? The other generators would be 3 times 3, which would be 9, 3 times 5, which would be 15, 3 times 7, which would be 21. So these would be the generators of the subgroup of order 8. Now, you might be saying, hold on, when we talked about this, we said it's a unique subgroup. Well, that's okay, because if I generate with 3, that's going to give me 3, and then 6, and then 9, and then 12, 15, 18, 21, back to the identity, right? So 1, 2, 3, 4, 5, 6, 7, 8. Now, if I generate with 9, I'm going to end up with 9, and then 18, and then 27, but remember that would be 3, and so on and so on. So we're going to end up actually generating the same subgroup. So it is a unique subgroup, but it can be generated by any one of these 4 elements. So these are the 4 generators for the subgroup of order 8. Now let's take a look at the Euler Phi function. The Euler Phi function is just this first paragraph. And essentially it's saying that phi of 1 is going to be equal to 1, and then for any integer greater than 1, phi of n is going to denote the number of positive integers less than n and relatively prime to n. So essentially, we're familiar with this already. We've been doing this with u of n since chapter 1. So u of n is the same as phi of n. So if we think about 8, say u of 8, 8 would include any values that are less than 8 but relatively prime to 8, so they don't share a factor. So 2 would not be, 4 would not be, because they share a factor of 2, but 5 would be, 6 would not be, but 7 would be. So u of 8 is 4, which means phi of 8 is 4. So if D is a positive divisor of n, the number of elements of order D in a cyclic group of order n is phi of D. So for instance, in Z24, if we want to find the number of elements of order 8, well, essentially we've just found it. So how did I do it? We're saying in Z24, so 24 is n, and 8 is certainly a positive divisor of 24. The number of elements of order D, so in this case D is 8, in a cyclic subgroup of n, of order n, is phi of D. So again, phi of 8 is 4, so it says find the number of elements of order 8. There are 4 elements. Now, does it say how to find them? No, it doesn't say how to find them, but we've done some work with Z24, and we found just moments ago that 3 would generate, and 9, and 15, whoops, and 21. Those are the 4 elements of order 8. So the elements themselves would obviously just be 3, 9, 15, and 21. I wanted to throw in a few practice for us to go through together because chapter 4, like least favorite chapter, just because it's so chock full of theorems with very little immediate application. So we're going to do a few practice together to make sure we understand the concepts. First practice, in Z30, how many elements have order 10? What are they? So remember, this is 10 is what we're looking at. 10 is a divisor of 30, so I'm looking for phi of 10, which is the same as u of 10. So what elements are less than 10 and relatively prime to 10? So that would be 1, not 2, 3, not 4, 5, or 6, 7, not 8, and 9. So phi of 10 is 4. So there's 4 elements of order 10. How do I find the elements of order 10? Well, that's where I'm going to take 30 divided by 10. So 30 divided by 10 to get 3. So one generator is 3. And the rest are in the form 3j, where again, j is relatively prime to 10. So 3 times 1 is 3. 3 times 3 is 9. 3 times 7 is 21. And 3 times 9 is 27. Next question. Suppose that the cyclic subgroups of A, B, and C are orders 6, 8, and 20 respectively. Find all of the generators. So again, how do I find all of the generators? Well, I'm looking at 6. I'm looking for numbers that are less than 6 but relatively prime to 6. So that's 1 and 5. So the generators of A are A and A to the 5th. What about 8? That would be 1 and 3 and 5 and 7. So the generators of B are A cubed, A to the 5th, I'm sorry, B, those should be B's. B, b to the third, b to the fifth, and b to the seventh. And then for 20, it would be 1, not 2, 3, not 4, 5, or 6, 7, not 8, 9, not 10, 11, not 12, 13, not 14, 15, or 16, 17, and 19. So to generate C, the generators would be C, C cubed, C to the 7th, C to the 9th, C to the 11th, C to the 13th, C to the 17th, and C to the 19th. Okay, last two practice. First, let G be cyclic and suppose that the order of G is 24. Let A be an element of G such that A to the 8th is not E, and A to the 12th is also not the identity. So show that the cyclic subgroup generated by A is in fact the entire group. So how do we go about this? Well, we know that the order of G is 24, which means that the order of A has to be a divisor. 1, 2, 3, 4, 6, 8, 12, or 24. Now it tells us here that A to the 8th is not E, so it's not 8, and A to the 12th is not E, so it's not 12. So let's just go through one by one. If, for instance, I chose an order of 1, well, if A to the first was equal to E, then A to the 8th would be E to the 8th, right? Which is just E. So it can't be 1. So let's look at 2. What about A squared? If A squared is equal to E, then A to the 8th would be the same as A squared to the 4th, which is just E to the 4th, which is E. So it can't be 2. Now let's look at 3. A to the 3rd is E. Then we could say that A to the 3rd to the 4th is E, because that's E to the 4th, but again, A to the 12th is not E. So it can't be 3. It can't be 4, because we could do the exact same process with 8 or 12, and it can't be 6, because we would do the same process with 12. So the only thing it could be is 24. So if the order of A is 24, then it's clear that that's the order of G, and therefore the subgroup generated by A has order 24 and therefore equals G. Last one, just a lot of kind of silly math. If G is an abelian group and contains cyclic groups of orders 4 and 5, what other sizes of cyclic subgroups must G contain? So again, we're going to let the order of A be 4 and the order of B be 5. Now it's abelian, so we know that AB to the 20th is equal to the same as A to the 4th to the 5th, and B to the 5th to the 4th. Well, A to the 4th is E, and B to the 4th is E, so that's just E. So we know that AB must divide 20. So if we look at, say, numbers that divide 20, just like we did above, 1, 2, 4, 5, 10, and 20. So let's start by looking at 4. If we said AB to the 4th, well, that's the same as A to the 4th, B to the 4th, but A to the 4th is E, so that's B to the 4th, but that doesn't equal E. So it can't be 4. And A, B, and in fact, it can't be 4 or 2 or 1, because those are the divisors, right? If I look at AB to the 10th, that would be A to the 10th, B to the 10th, but B to the 5th is E, so this is really A to the 8th, A squared, and then E squared, which doesn't matter. A to the 8th is E, so really my solution is A squared, which is not E, so it can't be 10 and it can't be 5, which is a factor of 10. So just as before, we can say that the order of AB must be 20. So if the order of AB is 20, It has subgroups of the factors of 20, which is 1, 2, 4, 5, 10, and 20. Up next, we're taking a look at permutations, composition, and cycle notation.